Hello everyone, and welcome to NSTA Web Seminars, where you can find live, interactive learning on your desktop. My name is Paul Tingler. I'm the Director of Web Seminars at NSTA, and I'll be moderating tonight's program. Joining me from Virginia is my colleague Jeff Lehman. Jeff is available to answer your technical questions during the live presentation. Our program tonight is part of the NASA Explore School series, and it is entitled Properties of Living Things, Searching for Life on Mars. And our presenter is Marty Phipps. Welcome, Marty.
I want to thank Paul very much. He is such an excellent host for all of these. He just does such an outstanding job on everything that I really want to thank him. And I do want to apologize to you a little bit in advance. It sounds like I'm getting a little bit of a, losing my voice just a little bit. So anyway, I'm going to go ahead and change this to yes or no answers. But anyway, I'd like to welcome everyone to the live presentation of Properties of Living Things, Searching for Life on Mars. My name is Marty Phipps, and I am the NASA Explore Schools Education Specialist. And I'm located at the Jet Propulsion Laboratory in Pasadena, California. And I want to welcome everyone tonight. Since I am working with NASA Explorer Schools, and I forgot to change the slide there. Oh, I thought I had a little poll right here. Here it is, right here. I'm going to go ahead and take this poll just out of curiosity. If you could give me a green check if you are currently a member of the NASA Explorer Schools, or a red X if you are not, so I kind of know where I'm going with this tonight and where to direct you for some extension activities. So if you could go ahead, and I'm looking up at the top. It looks like pretty even across the board. It looks like we have more that are not than are. Okay, great. That gives me some idea of what's going on here. So, okay, I'm going to go back and give you a little bit of introduction to what we're going to be doing tonight. First off, I want to let you know that this presentation is actually divided into two separate lessons. In order to get to the nitty-gritty, the meat of the presentation, the actual activity, we have to go through some preliminary work, and we're going to do both of those tonight. You'll also have to do this in the classroom. Students will need to come up with a working definition of life before they can do the observation, which is testing different soil samples for the presence of life. So in part one, students will use research to develop their criteria. The class can combine their ideas in a teacher-guided discussion, and then in part two, they will then use their definition of life to determine whether there is anything alive in 3 separate soil samples. They will make observations. They can draw pictures as they collect the data, the samples, the experiments. And I want to add a special little note here that as a teacher in the classroom, you do set the criteria. You know what you want the students to find, what you want them to define. So, go ahead and let the students know that. And you're going to adjust that according to grade level. Wording of the definitions, again, according to grade level. So again, and you will choose the extension activity that you want to do with this. I'm kind of gearing this toward middle school, but you can take this up or down, and I'm going to give you a lot of extensions that you can actually do that with. So again, just to review, use personal definitions of life to determine if life exists in 3 separate soil samples, and they will be making observations and illustrate those particular findings. So, national standards. Now, science's inquiry is not really a standard. I just kind of put that up there because a lot of this is on inquiry, okay? Chemical reactions, structure and function in living systems, cells and biological evolution, Earth's history. So as you can tell, this covers quite a few standards there. The objectives. What do we expect the students to be able to do after they have actually finished this particular lesson or while they're working on it? They should be able to form an operational definition of what life actually is, again, according to their grade level. They should be able to conduct the simulated experiment with the soil samples, and this is very similar to what our Mars Viking lander did when it went to Mars quite a few years ago, but anyway. Again, we went over these objectives once, and I think we've gone over them twice, so let's just go on. Again, students should be able to state relationships between soil samples using, again, their own operational definition of life. And they should be able to take that and making inferences about the possibility of life on Mars based on the data that they obtained from the soil samples. Okay. Now, as you can see here, I have a website, a URL for a video here.
We're not looking for aliens. We're not even looking for fossils. We'll be looking for bacteria or signs of bacteria. And the reason for that is because for most of the Earth's history, they have been the predominant form of life. The chances are it may be different from life on Earth, and therefore what we have to look for is it doing the same things that life does on Earth?
Water is a necessary component for life as we know it. So when we think about trying to understand life on other planets, one of our strategies is to understand the water.
We're focusing on Mars because Mars, in its early history, may have been a lot warmer and wetter than it is now.
It looks like there used to be flowing liquid water on the surface of Mars, but today there isn't any liquid water that we can find, or if there is any, it's very infrequent. We want to detect organics because organics are the building blocks for life. Organics are molecules that contain carbon, and we know that carbon is a central element that makes up our bodies and makes up life. So both Phoenix and the Mars Science Laboratory will search for organics on Mars. Phoenix is the next Mars lander mission. When we land on Mars, we're going to land in the North Polar region. That's about equivalent to Alaska latitudes on the Earth, or mid-Greenland. And our job is to land and dig down and sample the soils and ice that we'll encounter in that region of Mars.
Mars Science Laboratory will have sophisticated instruments which will be able to look at the mineralogy in much more detail, but also looking at minerals which either were formed by organisms, living organisms, or show signs that living organisms were around when they were formed. But we're not only focusing on Mars. There are other places in the solar system which may have subsurface water. Beyond the solar system, there are people who are looking at the planets, which go around distant stars, trying to analyze their atmospheres. There's no silver bullet. We've got to take all the possible approaches, or at least a large number of them, and put all the bits together to see where to look and what to find. Looking for life outside the Earth, to find out whether we're alone or not, hey, what better job could there be?
You can also download it and you can show it in your classroom too. It's really an awesome video. But anyway, during the next 2 decades, NASA will conduct several missions to address whether life ever arose on Mars. The search begins with determining whether the Mars environment was actually ever suitable for life. With Curiosity, that's the Mars Science Laboratory that we just launched, or NSL as we call it for short, NASA's scientific goal is to explore and quantitatively assess a local region on Mars' surface, which of course is Gale Crater, as a potential habitat for life, either past or present. The NSL rover actually carries 10 scientific instruments on board. The various elements will work together to detect and study potential sampling targets and to acquire samples of rock, soil, and atmosphere, analyze them using onboard analytical instruments, and to observe the environment around the rover. I know that there's usually a lot of questions that come up about Curiosity. I will answer some of them at the end of the session today if you have questions on Curiosity. But we do have another presentation that's called Calculator Controlled Robots, where I do go over a lot of information about Curiosity at that time. So anyway, moving on with this particular presentation, I am going to tell you about one more mission that is actually in the works at JPL right now. And right now, I'm going to give you a year, but you know how NASA is with years. They hardly ever keep the dates that they plan on doing these things. It's just things just keep getting pushed forward. But somewhere in 2018 or in a few years past that, we have a mission plan that is yet to even have an official name. And eventually, when we get ready to name it, we'll throw that possibility out into the classroom. But what NASA hopes to do is to actually go back to Mars and actually return samples to Earth, and we've never done that before. Okay, but we actually have that mission in the works right now, so that's kind of exciting. Okay, we're going to start with the Phoenix mission. I'm just going to give you a little bit of history on what we've done with Mars to date before we actually get into the lesson. So just give me just a little bit of time here. The goal of the Phoenix mission was actually to answer 3 questions. Number 1, can the Martian Arctic support life? Number 2, what is the history of water at the landing site? And number 3, how is the Martian climate affected by polar dynamics? That's what Phoenix was sent to do. Now, during its mission, Phoenix actually confirmed and examined patches of the widespread deposits of underground water ice that was actually originally detected by Odyssey. And Phoenix also identified a mineral called calcium carbonate that suggested occasional presence of thawed water. The lander also found soil chemistry with significant implications for life and observed, are you ready, falling snow. The mission's biggest surprise was the discovery of something called perchlorate, which is an oxidizing chemical on Earth that is food for some microbes that potentially toxic for others. Okay. Another couple of missions that we would like to talk about here is on the left, the Mars Reconnaissance Orbiter actually reached Mars in 2006 and began a 2-year primary science mission. Its data showed Mars has a diverse wet environment at many locations for differing durations, that's a mouthful to say, differing durations during the planet's history. And climate change, those climate change cycles are actually present today. The mission has returned more planetary data than all the other Mars missions combined. We're very thrilled with that one. Odyssey on the right has been orbiting Mars since 2001 and has played an important role by supporting the twin rovers, Spirit and Opportunity. Okay. Now, examples, if we take a look at Earth, examples of life are everywhere. You can find living organisms from the poles to the equator, from the bottom of the sea to several miles in the air, from freezing waters to dry valleys to undersea thermal vents to underground groundwater thousands of feet below the Earth's surface. Over the past 3.7 billion years or so, living organisms on the Earth have actually diversified, and they've adapted to almost every living environment imaginable. I know that there was one biologist that tracked, I don't know how many different versions of finches in this one South Pacific island, and at one time they were all the same, but basically they adapted to their environment, and so they had different varieties of finches there. It's amazing what life can actually do. Now, Mars is more like Earth than any other planet in our solar system, but it is still very different. You would have to wear a spacesuit to provide air and to protect you from the sun's rays, because the planet's thin atmosphere does not block harmful solar radiation. Your spacesuit would also have to protect you from the cold temperatures on Mars, which very rarely climbs above freezing. They can get as low as 200 degrees below 0 Fahrenheit, so it's very cold. You would need to bring water with you, although if you brought the proper equipment, you might be able to just get some Martian water from the air or the ground itself. Now, the Martian surface is dusty and red, and it is notorious for its huge dust storms that just rage across the surface of Mars. It can darken the planet for days on end. It's not like the dust storms that we have on Earth, which kind of come and go. These last for quite some time. Instead of a blue sky, you can see a dusty pink sky that would probably hang over the top of you. And again, the reason for that is because the wind is blowing so much of that dust, the Martian dust, up into the atmosphere, so it gives the atmosphere that reddish haze to it. Okay. Now, more than 30 years after NASA's Viking landers found no evidence for organic materials on Mars, scientists say a new experiment on Mars-like soil shows Viking may have, in fact, hit pay dirt. The result was not initially understood due to the strong oxidation effects of salt in the Mars soil, known again, remember that word perchlorate? However, this August, in 2008, discovery of the powerful oxygen-busting compounds at the landing site of Phoenix prompted a new study. However, all reports do not absolutely confirm the presence of perchlorate in the Martian soil. Plus, there is a remote possibility that Phoenix actually may have carried them to the planet. Although the retro rockets landing Phoenix did not contain perchlorates, the vehicles used to launch Phoenix, that was the Delta II rocket, may actually have done that. So what is this particular substance that I'm talking about? Perchlorate is actually made up of chlorine atom bonded to 4 oxygen atoms and is actually an oxidizer. If that or any other oxidizers are abundant in the surface soil layers on Mars, this is not a good sign for finding signs of past or present life on Mars, near the surface anyway. Prolonged exposure to these oxidizing agents, not to mention the ultraviolet or cosmic rays, would destroy almost all the organic molecules, leaving little or no trace of organics for us to actually pick up. So we have a lot to work with here. Mars rovers. Okay, these are probably a few of the ones that you're familiar with. We have the NASA's twin robotic geologists. We love these guys. MER, or the Mars Exploration Rovers, launched toward Mars on June 10th and July 7th in the year 2003. And you all know that they lasted much, much longer than they were meant to. But they were to search for answers about the history of water on Mars. Their assignment was actually to follow the water. Where is the water? They were following the water. Primarily, among the mission scientific goals was to search for, and again, characterize a wide range of rocks, soils that held clues to past water activity on Mars. The spacecraft are targeted 2 sites on opposite sides of Mars that appear to have been affected by liquid water in the past. Now, if you are part of the NASA Explorer School system and you know what a NASA Now is, we actually had one of our education specialists, Nadine Cox, actually did a NASA Now on Spirit and Opportunity and Follow the Water. So if you haven't seen that yet, you might go onto our site, our virtual campus, and actually view that NASA Now. For the rest of you, I'll talk more a little bit later on about what that is and what I'm talking about here. Curiosity, the robot to the right, is in transit to Mars right now. We expect Curiosity to land on Mars, arrive at Mars sometime in August of 2012. Curiosity is much different than any of the other rovers that we have sent to Mars, even though it looks the same. Curiosity is about the size of a Mini Cooper. It's pretty big, and it's nuclear powered. It doesn't rely on solar energy. Another really good thing about Curiosity is Curiosity does not have to actually go up to a rock to examine it. It has a laser that it actually shoots at the rock, and the gases from the rock go up into the air, and Curiosity's instruments can actually analyze that gas. And so it can zap all of these rocks, and then it can figure out which one it wants to go over to and actually analyze a little bit closer. So it's pretty neat. It has 10 science instruments on board to search for evidence about whether Mars had environments favorable to microbial life, including the chemical ingredients for life. Again, we're very excited about Curiosity, and in August, I invite everybody to watch that particular landing. We're going to be landing Curiosity completely different from anything else that we've ever landed on the surface of Mars. It's not going to go down in a bouncy ball. It's actually going to be lowered a little bit differently. So if you haven't seen that yet, you need to watch Curiosity as it lowers itself to the surface of the Mars. And this is a precursor, hopefully, to actually eventually sending humans to Mars, because we probably want to land them close to the same way. Okay, I put this picture in because I really like this picture. In the background, you can see those offices. Actually, that's for my offices. That's the education department located down there at JPL. And we actually have 3 of our rovers lined up right out front our steps here. We have Sojourner that went to Mars in 1997, and you can see how small Sojourner was compared to Spirit and Opportunity. Spirit and Opportunity is if you look at Sojourner, it's quite a bit bigger. And of course, they went to Mars in 2004. Now, if you take a look at Spirit and Opportunity, and then you compare that to Curiosity, you can see that we're getting bigger, we're getting better. We know what we're doing now, and we keep expounding on what it is that we want to do and what we want to find. And now that I've said that, I will add that every single mission to Mars is actually decided on by the previous mission. Okay, so basically the information that Sojourner sent back to us determined what we were going to have Spirit and Opportunity do when it got to Mars. What we learned from Spirit and Opportunity determined the mission for Curiosity. So each one of these it tells us exactly what we want to do for our next particular mission. Okay. Now, I have a little quiz here for you, just real quick, and I'm going to have you just type these answers into the chat window. I talked about several different types of spacecraft. Didn't give you names, I just talked about different ones. Can you name 3 types of spacecraft that we have sent to Mars? And just give me the answers in the chat window. I'll give you about 90 seconds to do that. Who's going to be up first? What are the 3 types of spacecraft? Oh, gee, orbiter, lander, and rover. Susan, how did you guess that so quickly? Yes, you guys are so totally awesome. You're so smart. Look at that. Look at you guys. Yes, take a look at the next question. It's a little bit harder, and I wonder where you got orbiter, lander, and rover. Now what I want you to do is to give me the name of an orbiter. Can you give me a name of an orbiter? What is the name of an orbiter? Okay, Mars Reconnaissance Orbiter. Good, good, great. Okay, give me the name of a lander. What was the name of the lander? I mentioned one. The Phoenix. Good. Phoenix, great. And give me the name of at least 3 different rovers. I want 3 different rovers. Oh, you guys are ahead of me. You already had that typed in, Carolyn. Great. You guys are totally awesome. Such a great audience you are, too. And I thank you for playing on with me, participating. I think that is totally awesome. So I'm going to pause for just a moment, Paul, and hand it back to you for questions.
Thank you, ma'am, and thank you for that information in the beginning, and always a wealth of information there about the different Mars rovers. And if you have questions on any of that information or the rovers or anything in the intro there, please do go ahead and place that in the chat at this time, and we'll pass it along. And I see why does have a question popped up right away there. It says, are the soil samples come from Mars?
No, we haven't actually returned anything from Mars yet. I'm going to show you how to make your own soil samples, and again, just a little bit of heads up on that. You're going to put the soil samples together before the students ever come into the classroom. You don't want them to know what you're actually putting into the soil. We do want them to find some kind of life. Yeah, actually you are using soil, where you're just adding some things to the soil. Okay. Any more questions? So, from what Viking, the pay dirt. That'll have to be the next live presentation. Name of that, perchlorate? Perchlorate? How can we watch the landing of the Curiosity? I tell you what, if you, a couple of different ways that you can do that, or actually 3 ways. You can either stay with me or come back with me during the presentation of calculator-controlled robots. You can email me for the URL, and I will give you my email address at the end of today's session. Or you can just go on to the JPL website and type in Curiosity, and you can get it that way. Okay? Yeah, we have a huge website on Curiosity, yes, and it has all kinds of videos on there. Okay? Great. Any more questions? Okay. I'm going to go ahead and move on then, and if you think of anything else, there will be more time for questions a little bit later on. So I told you that this is going to be broken down in 2 different lessons, and so we're going to talk about the first lesson again. And again, keep in mind that you're going to adjust this according to the grade level that you teach. I have the wording geared to probably 4th, 5th, 6th, 7th, 8th, somewhere in there, okay? But depending on the age group, again, you need to give them something they can actually relate to. For example, you might say this, okay? Alive or not alive, okay? Consider a bear and a chair, okay? They both have legs, but one can move on its own. The other would need a motor made by humans. Therefore, independent movement might be one characteristic that indicates life. Yeah, not every organism needs legs or roots, but they do need a mode of locomotion or a way to get nutrients. Also, the bear breathes and the chair does not, another indication of life. Or consider a tree and a light pole. We know that a light pole cannot reproduce, and it's made by humans, and we know that the tree makes seeds that they may produce more trees. The tree also takes in nutrients and gives off gases and grows. The light uses electricity, gives off light, but is strictly an energy exchange, and there is no growth, there's no metabolic processes there. Okay, no, according to all I teach, okay? So you're saying that movement is not required of any kind? Okay, yeah, we'll talk about that. Let's talk about that. I'd like to know where you're going with that. I'm very, very curious, okay? So if you have time, okay, I would love to talk to you, okay? Conditions. In order for life to evolve, the planet needs both water and energy. There are 2 forms of energy, chemical and geothermal. Chemical energy is the potential of a chemical substance to undergo a transformation through a chemical reaction or to transform other chemical substances. Geothermal is thermal energy that is generated and actually stored in the earth. Okay. If life once existed, it's going to leave a biosignature. And that biosignature, what we expect it to be, is in the form of carbon. A biosignature is any substance, such as an element, an isotope, a molecule, I guess, or a phenomenon that provides scientific evidence of past or present life. Okay. Now, we usually recognize something as being alive or not alive, but when scientists study very small samples or very old fossilized materials, those signs of life or previous life are not as easy to determine, okay? I mean, you look out the window, you look out the door, and you say, well, that's alive, that's not alive. But again, some things that scientists are trying to determine if it was once alive, it's not quite that easy. So what they have to do is they have to establish some type of criteria to work with in their research. The tests for life, for example, used by the Viking Mars missions were based on the data that life would cause changes in the air or soil in the same way that life on Earth does. The Viking test did not detect the presence of life on Mars, The Viking tests would not have detected fossil evidence of past Mars life or a life form that is very different from anything on Earth. That's not what it was. Okay. There's a lot of conversation going on in the window. I hope there's no questions to me. If there is, I can get back to those a little bit later on. Okay. Anyway, again, we do have some discussion questions here, and maybe this is where we need to go with the chat window. Okay, so let's just have some chat here. For example, number one, what are some characteristics of living things? Go ahead and give me some answers in the chat window. What do you think? And remember, we have all grade levels here. Okay, all the way from elementary to middle school to high school, and I think I saw some college here. Okay, they're made up of cells. They can reproduce. Okay, replicate. Good. Okay, what are some other characteristics? They grow. They develop. Okay, good. Irritability. I love it. Okay. Great. Exchange gases. Okay, we've got a lot of different things going there. So, okay, great. So, and I can see by the vocabulary, again, I'm getting a lot of different grade levels in there. What we would expect someone from, say, 5th and 6th grade to answer as opposed to high school, you know, again, completely different. And it's a teacher-run classroom, so you're going to be in charge of that. Let's look at the next question. Okay. What are some characteristics of non-living things? Okay. Why would you look at something and say, okay, you know what, that's not alive? Matter. Okay. DNA, man-made. Okay, is it all man-made? Okay. Cool. Container cells. Okay, good. You guys are coming up with some excellent things there. All of these are totally great. Let's move on to the third question now. How are living things different from non-living things? Okay, a lot of you, I mean, some of the answers are duplicated, but that's okay. You guys catch where I'm going with this. This is the kind of a discussion that you need to be having in the classroom with your students. They need to understand the criteria. They need to come up with something that is workable for them. Okay, the difference between alive and not alive. Okay. And so the next thing that I would basically do is we would come up with a chart, something that looks like this, fundamental criteria for life chart. Now, I again have done this according to, I think, 6th, 7th, and 8th grade, and this is some of the criteria that we came up with for them and some of the wording. Again, you would probably adjust the wording. But a criteria could be, number one, react to its environment. And again, these are in no particular order. Must react to its environment, adapt to its environment, and this is one that you guys kept coming up with, is reproduce. It must replicate, reproduce, make more of its own kind. Okay. Grow. Okay. Obtain and use energy of some kind. Okay. And it must be made up of cells. And you guys were excellent because I kept seeing these coming up in the, let me go back one. I kept seeing these come up in the chat window. I think that at one time you guys hit every single one of these. So again, my hat's off to you. I think you should all give yourself an applause. So let's go up to the top, and I want everybody to find the smiley face, go down to the applause, and give yourself a little hand on the back there. Okay? And what I'm going to do now is, I know that we had, I don't know if we had questions or not, but I'm going to turn it over to you, Paul.
Thank you, Marty. Once again, there have been a lot of comments in response to the information that she was talking about earlier, and we thank you very much for doing that. Just a large number of comments, and if you had trouble keeping track of the chat because of that, then don't dismay. But if you ask a question in that, because it was firing through so fast, we probably missed it. So any questions that you have that are related to the information that we've been talking about here with some of the characteristics of life as well as others, and please go ahead and drop those into the chat at this time so that we can focus on the particular questions and not just the commentary and responses. And I see the first one there from Carolyn. Would life on other planets have a cellular base? Marty?
Whoops, I just lost the question. Let me scroll back up here. Would life on other planets have a cellular base? You know what, that's hard to answer a question like that because we know what the Viking was looking for, but we hesitate to put an identity on something from another planet. You know, some of the scientists at one time said, you know, we have to kind of think out of the box. We shouldn't say just because this is what life on Earth has, that when we go to another place, another planetary body, that life there would resemble what we expect here. As a matter of fact, we follow the water, we look for water, but is water mandatory for every kind of life form out there? You know what, I would hesitate to answer that question. And there was a whole bunch more that looked like they fly are not made up of cells. Did I miss anything here? So would all the other characteristics of life apply? Okay, it looks like everybody there was answering my question for me. Okay, that rotates. Okay. If I missed your question, and I probably did, I'm scrolling back up, but every time a question comes back in, I pop back down to the bottom of it again. What about gas exchange? That's, I think, let me go back to the list of criteria. If you take a look at this, react to its environment, reproduce, grow, obtain and use energy, yes, that would probably fit into that particular category. Reproduction, for life to continue but not for life to exist. Yeah, that's true, but you know what, if we want to, you know, continue to find it, we really do expect it to reproduce. Okay. The no living things compose inorganic materials. The no living things and eliminate waste. Okay, it looks kind of like you guys are answering a lot of the questions yourself. I am going to hang around at the end of the session today for all of the questions that that you have. Yes, Susan, I can tell you teach that. I probably learned a thing or two from you. That's why I want to talk to you, Plasma Cells. Okay, anyway, I'm going to go on, and I think that there probably were a lot of things that questions that you asked. But I don't know if Susan or some of the rest of you were answering them in the chat window. But again, hang around, and I will be more than glad to talk to you at the end of today's session. I do want to make sure that we actually go over the actual project here. And the project is coming up next. Okay? And this is what this lesson is mainly about. And again, you gear this towards your own classroom. I have geared this toward 6th, 7th, and 8th. Okay? Good question. Universal solvents besides water. Well, I don't know. That might be a Susan question there. Okay. What you're going to need for this particular project is, first of all, you're going to need sand or sandy soil of some kind. I've actually mixed a couple of different kinds of soil, but I did put sand in it, but I think I put some soil in it too. I want a lot of different things, so the students have a hard time, you know, saying that this is what this is, this is what this is, this is what this is, okay? You need some glass vials, baby food jars work fine, beakers. Anyway, you need 3 glass vials for each particular group that you're using. Okay, or that you're breaking them down into, because you want the sandy soil samples in all 3 vials. Okay, I'm going to stop talking so much now. Here we go. You need 5 milliliters of sugar, which will be added to the soil. You need instant active dry yeast. You guys are probably catching on now. 5 milliliters will be added to 50 milliliters of soil, and you need some Alka-Seltzer tablets that will be crushed, completely crushed. You don't want to see any large little pieces of Alka-Seltzer, because trust me, those kids will be able to identify it if they actually see it, okay? But anyway, these are the materials that you're going to need, and a little bit more about, and just the first one is a suggestion. You're going to need hot water, warm water, but you don't want it hot enough that it's actually going to kill your yeast, okay? If you get it too hot, that's going to happen, and you're not going to get the reaction in that one particular container that you want, okay? You're going to put water in each of the containers, and you're just going to put just enough water to cover the tops of the soil in all 3 of your jars. You need cups for distributing the water. You need enough magnifying lenses so that each group can have at least 1 or more. And you need a copy of recording sheets, and I'll show you what those look like in just a minute or 2. Okay, what the students are going to do is they will take 3 different soil samples, and they're going to look for signs of life based on the criteria that you guys came up with earlier. Again, you can come up with your own criteria. You can make it as easy or as difficult as you want to do, but that depends on your age group. Okay, and we have 2 data charts that are available in the Educator's Guide, and I will give you the website for the Educator's Guide before the end of the lesson today too, so you'll actually have that. The first one, the first data chart, is no water added. Now again, you're going to put these 3 samples together before the class comes in. You're going to have, you know, one sample that they're all 3 going to have sugar in them. One is just going to have sugar, the second one is going to have sugar and Alka-Seltzer, the third one is going to have sugar and yeast in it. Again, give them magnifying lenses and tell them to have at it. They can take the soil out, they can look at it. They write down what it is that they think they see. They write down, do you see life, do you not see life? Okay, what is it that you see? Make your observations. And then you have them add water to each of the soil samples, and then you have them make observations again. And as you know, things are going to actually react. Oh good, I did have this broken down for you. Okay, again, jar 1, you're going to fill it with 50 milliliters of soil, and you're going to add 5 milliliters of sugar to that. In jar 2, 50 milliliters of soil and 5 milliliters of instant active dry yeast and 5 milliliters of sugar. Okay, and then in jar 3, instead of yeast, you're going to use the powdered Alka-Seltzer, and again, grind that down very nicely so they can't actually see what's going on in those containers. And again, what they'll notice is they especially between the Alka-Seltzer and the yeast, when you add the water to the Alka-Seltzer, we all know what's going to happen. And the students, the younger students especially, what they're going to think is that, oh my gosh, you know what, there's actual life in this. What is it? What is it? And then when they did the same thing to the yeast, it's a little bit slower in starting, but it keeps growing and growing and growing. And you can have them go back to the soil sample with the Alka-Seltzer. Well, what's it doing now? Well, it's not moving so much. It's not reproducing. It's not doing some of the things that it was doing in the beginning, but then when they go back to the soil sample, and it's kind of like out of control now. So it's a very good discussion moment on what the difference between alive and not alive that you can have in the classroom. So anyway, what we do have available to you out there on our NASA Explorer School website, and you see their website right there, it's explorerschools.nasa.gov. For those NASA Explorer School people out there, you can go into this particular lesson and download the student PowerPoint. We've already put a student PowerPoint together for your use in the classroom, and so you can go here and actually get your own student PowerPoint that you don't have to put together yourself. Okay, and this will go through the project for your students ahead of time, so that's really good. Okay, and what we have here is I've got some extension activities, and this is where you can bring in the younger kids or the older kids. We've got Getting There, which is navigation and trajectory, with tricky terrain, investigating planetary soils, layer law. Okay, having trouble talking. Lava layering. And we also have mapping Mars. And what I have here is a website, and I'm having trouble with my computer freezing up on me, so I actually hesitate to take people there, Paul. But if you could help me out here, I will go ahead and put it in the chat window. If you could bring this up and put 5 minutes on the clock for me, I'm going to let our audience investigate this particular website for about 5 minutes. So could you do that for me, Paul? Thank you.
All right, folks, you should see the website up there now in the browser, and there's a PDF that you are to browse during the time. We have the timer set, so go ahead and take a look at that, and then if you want to make comments as you take a look at it, Marty has also put it in the chat as well. It is also part of the collection, so don't feel obligated to have to save it, but you're welcome to bookmark it if you'd like and return to it, but again, it will be part of the collection that will be on the website tomorrow as well.
Thank you, Paul, for doing that for us. Now, as you can see, that was the educator guide, and I know 5 minutes is probably not long enough for you to discover everything that's in there, but it's a phenomenal set of resources there. A couple of the other websites that I wanted to give you is, first of all, NASA's Explorer School Virtual Campus. You've heard me mention NASA Explorer School several times. Now, if you are actually an educator in the classroom, you are welcome to join the Explorer School system, and you have access to our virtual campus. The website is there, www.explorerschools.nasa.gov, and I will put that into the chat window for you in just a little bit. There is also another website that I'm going to place into the chat window. And we aren't going to go there and take a look at it right now, but it will be archived. There it is. It just now showed up. And you can actually access that one too, and you can find many, many more extensions and activities and things like that. I do have one more, however, that I want to give you just a little bit of time. And I think we're going to have time to do this. So this is another website. Paul, if we could take everybody here and give them about, let's give them about 4 minutes to look around, okay? That would be great. Again, thank you very much, Paul. And I'll move on. Anyway, again, if you are with the NASA Explorer School system, make sure that you go back onto the virtual campus and you log your participation for tonight's lesson on searching for life on Mars, and make sure that you get the credit for that. The rest of you, again, if you're an educator in a classroom, you can go to the virtual campus and sign on, and then you can also log in your participation and get your credit for that. We also, again, if you're a NASA Explorer School person, you can get your continuing education credits from Oklahoma State University, and by participating in 7 live web seminars and completing the surveys on the virtual campus, for each one you can earn 1 CEU. For completing 14, you can earn 2 CEUs. And we have just a little bit more information about the CEUs there. They must be done between those particular dates. So one of the things that I invite all of you to do is you can actually friend us on Facebook, NASA Explorer Schools. We have a site on Facebook. We have a site dedicated to each one of our live presentations and properties of living things, searching for life on Mars. Is actually there. So when you actually use this in the classroom, we would really appreciate you getting onto Facebook and writing your experiences down, sharing what you did, and I'm sure that you guys are going to come up with some totally awesome things, some things that we did not talk about during the presentation tonight, and it would be really great if you could get onto Facebook and share those with us. And we look at those every single day, so it's not like we're telling you to do something that we're not going to look at. We really do. So be our friend on Facebook. We also, you can follow us on Twitter. We also have NEON, which is a collaborative community that teachers get on and talk back and forth about how they can help each other. And as you look and see down here, we have some of our live presentations listed here. There's calculator controlled robots down there, which is another one that we do. So at this point, I'm going to stop and ask if there is any questions with what I've given you so far. So Paul, I'm going to go ahead and turn it over to you.
Thank you, Marty, and go ahead and see if you have any questions, or even if you'd like to make some comments on the resources. Some of you did as you went along there, but if you have others or have other questions about the resources that we shared there that give you a chance to browse those, then please go ahead and do place those in the chat at this time as well, as we do appreciate hearing that. And thank you, Y, and others who commented about the usefulness of those resources. But again, if you do have questions, then go ahead and shoot those out, and Marty will respond. Yes, Susan, that's true that you have to wait until you get home to actually do anything with Facebook and Twitter, but I guess par for the course in how we run things. Janine, I'll let Marty go ahead, because it sounds like you're asking that from the NES perspective.
I want to thank you all for joining me tonight. It's been a pleasure being here with all of you. You're totally awesome. Paul and Jeff, you're as awesome as always. Come back to the virtual campus, the NES virtual campus anytime. Share your experiences again on NEON. Join us during live presentations or live seminars. If you see down at the bottom down there, I have given you my email address, and I will type that email address into the chat window. You guys feel free to contact me with any and all questions that you have, and I will respond to all of them, okay? So again, thank you very much. So, okay, Paul, it's all yours.
Thanks, Marty. Before I close, I just wanted to mention Janine had asked a question about documenting things on the Explorer School website. So if you could just review that quickly before we move into the close.
Okay. Yes, absolutely. I'm sorry I missed that question. I guess that things were coming in too quickly for me there. But what you will do is, if you are, again, a participant of the NASA Explorer Schools, go back into the lesson library, and you will find this particular seminar, Properties of Living Things. What you want to do is to go back into that lesson, and you will actually see, let's see, something that looks just like this. It has a little survey thing down there. If you click on that, it will actually let you take the survey, and that way you can log your participation and you can get your credit, because we actually do some pretty awesome things with our schools during the summer. Our teachers, we have recognition, teacher recognition, student recognition, and school recognition, and that all applies toward that. So anyway, go back and log on to that.
All right, thank you very much, and we will go ahead and move to close here. So we do like to thank our sponsor of tonight's program, NASA. I'd like to remind you to join us in the Learning Center, where you can register for future web seminars, as well as take advantage of the over 7,000 now EPD resources for your professional development, many of which are absolutely free, including the web seminars. And so we do hope you will join us and take advantage of that, and particularly join us on our discussion forums and discuss a number of different topics, like the larger general science topics. But if you would like to start a discussion within those on web seminar of particular interest, then that would be also acceptable as well. We'd like to thank the administration of the National Science Teachers Association for their support for web seminars.
And I'm looking up at the top. It looks like pretty even across the board. It looks like we have more that are not than are. Okay, great. That gives me some idea of what's going on here. So, okay, I'm going to go back and give you a little bit of introduction to what we're going to be doing tonight. First off, I want to let you know that this presentation is actually divided into two separate lessons. In order to get to the nitty-gritty, the meat of the presentation, the actual activity, we have to go through some preliminary work, and we're going to do both of those tonight. You'll also have to do this in the classroom. Students will need to come up with a working definition of life before they can do the observation, which is testing different soil samples for the presence of life. So in part one, students will use research to develop their criteria. The class can combine their ideas in a teacher-guided discussion, and then in part two, they will then use their definition of life to determine whether there is anything alive in 3 separate soil samples. They will make observations, they can draw pictures as they collect the data, the samples, the experiments. And I want to add a special little note here that as a teacher in the classroom, you do set the criteria. You know what you want the students to find, what you want them to define. So, go ahead and let the students know that. And you're going to adjust that according to grade level. Wording of the definitions, again, according to grade level. So again, and you will choose the extension activity that you want to do with this. I'm kind of gearing.
Hello everyone, welcome to NSTA Web Seminars, where you can find live, interactive learning your desktop. My name is Paul Tingler. I'm the Director of Web Seminars at NSTA, and I'll be moderating tonight's program. Joining me from Virginia is my colleague Jeff Lehman. Jeff is available to answer your technical questions during the live presentation. Our program tonight is part of the NASA Explore School series, and it is entitled Properties of Living Things, Searching for Life on Mars. And our presenter is Marty Phipps. Welcome, Marty.
I want to thank Paul very much. He is such an excellent host for all of these. He just does such an outstanding job on everything that I really want to thank him. And I do want to apologize to you a little bit in advance. It sounds like I'm getting a little bit of a, losing my voice just a little bit. So anyway, I'm going to go ahead and change this to yes or no answers. But anyway, I'd like to welcome everyone to the live presentation of Properties of Living Things, Searching for Life on Mars. My name is Marty Phipps, and I am the NASA Explore Schools Education Specialist. And I'm located at the Jet Propulsion Laboratory in Pasadena, California. And I want to welcome everyone tonight. Since I am working with NASA Explorer Schools, and I forgot to change the slide there, well, I thought I had a little poll right here. Here it is, right here. I'm going to go ahead and take this poll just out of curiosity. If you could give me a green check if you are currently a member of the NASA Explorer Schools, or a red X if you are not, so I kind of know where I'm going with this tonight and where to direct you for some extension activities. So if you could go ahead and toward middle school, that you can take this up or down, and I'm going to give you a lot of extensions that you can actually do that with. So again, just to review, use personal definitions of life to determine if life exists in 3 separate soil samples, and they will be making observations and illustrate those particular findings. So, national standards. Now, science's inquiry is not really a standard. I just kind of put that up there because a lot of this is on inquiry, okay? Chemical reactions, structure and function in living systems, cells and biological evolution, Earth's history. So as you can tell, this covers quite a few standards there. The objectives. What do we expect the students to be able to do after they have actually finished this particular lesson or while they're working on it? They should be able to form an operational definition of what life actually is, again, according to their grade level. They should be able to conduct the simulated experiment with the soil samples, and this is very similar to what our Mars Viking lander did when it went to Mars quite a few years ago, but anyway. Again, we went over these objectives once, and I think we've gone over them twice, so let's just go on. Again, students should be able to state relationships between soil samples using, again, their own operational definition of life. And they should be able to take that and making inferences about the possibility of life on Mars based on the data that they obtained from the soil samples. Okay. Now, as you can see here, I have a website, a URL for a video here.
We're not looking for aliens. We're not even looking for fossils. We'll be looking for bacteria or signs of bacteria. And the reason for that is because for most of the Earth's history, they have been the predominant form of life. The chances are it may be different from life on Earth, and therefore what we have to look for is it doing the same things that life does on Earth?
Water is a necessary component for life as we know it. So when we think about trying to understand life on other planets, one of our strategies is to understand the water.
We're focusing on Mars because Mars, in its early history, may have been a lot warmer and wetter than it is now.
It looks like there used to be flowing liquid water on the surface of Mars, but today there isn't any liquid water that we can find, or if there is any, it's very infrequent. We want to detect organics because organics are the building blocks for life. Organics are molecules that contain carbon, and we know that carbon is a central element that makes up our bodies and makes up life. So both Phoenix and the Mars Science Laboratory will search for organics on Mars. Phoenix is the next Mars lander mission. When we land on Mars, we're going to land in the North Polar region. That's about equivalent to Alaska latitudes on the Earth, or mid-Greenland. And our job is to land and dig down and sample the soils and ice that we'll encounter in that region of Mars.
Mars Science Laboratory will have sophisticated instruments which will be able to look at the mineralogy in much more detail, but also looking at minerals which either were formed by organisms, living organisms, or show signs that living organisms were around when they were formed. But we're not only focusing on Mars. There are other places in the solar system which may have subsurface water. Beyond the solar system, there are people who are looking at the planets which go around distant stars, trying to analyze their atmospheres. There's no silver bullet. We've got to take all the possible approaches, or at least a large number of them, and put all the bits together to see where to look and what to find. Looking for life outside the Earth to find out whether we're alone or not? Hey, what better job could there be?
You can also download it and you can show it in your classroom too. It's really an awesome video. But anyway, during the next 2 decades, NASA will conduct several missions to address whether life ever arose on Mars. The